For chapter 4, we're going to be writing the Fibonacci sequence. And this is going to get us into what it's like to write, test, and benchmark algorithms. So an algorithm is, a repeatable method of doing something, and there are lots of ways of writing a Fibonacci generator, and we're going to talk about a few of them, and then we're going to try to figure out which one is the best for some given value of best. And if we start off by looking at the Fibonacci description here from the Rosalind page, we'll see that it has a pretty mathematical definition of what it looks like. But the important part is that our program is going to take two integers, n for the number of generations that we're going to create, and k for the size of the litters. And so this problem actually comes from the observation about breeding rabbits. And so a lot of times the Fibonacci sequence, it just uses a k value of 1, but we have to write a program that will take a variable number of rabbits that are produced at each one of these generations. And our program only needs to go up to a maximum of 40. So this is the first program we're writing that's going to take integer values, and they need to be in a particular range. So given an input of 5 here for the number of generations and 3 for the litter size, the output of our program should be 19. So if you think you know how to write the program, you should go off and do that now, and then come back and compare notes with me. If you want, I will walk you through a few solutions, and we can figure out how to write this. So, like I said, it comes from some simulations of breeding rabbits, and it has some very important but unrealistic assumptions. The first month starts with a pair of newborn rabbits, and they can reproduce after a month. And then every other month, every rabbit of reproductive age mates with another rabbit of reproductive age, and they, exactly 1 month later, they produce a litter of the same size, and the rabbits are immortal and they never stop mating. So obviously this doesn't actually hold with reality, but it's an interesting sequence of numbers. And what makes it interesting is that it generates itself, it continues to generate from itself. So we generate the next value by adding the previous two values in the list. The list always starts off with 0 and 1, and then from there it grows with a litter size of 1. It grows like this: 1, 2, 3, 5, 8, 13, 21, and so on. If you were to search for solutions for this, you will find so many, and so they go down so many rabbit holes, if you will pardon the pun. And there's many, we're going to talk about the differences between an imperative generator and a recursive solution, and what that means. And so what we'll be learning along the way is, first off, we need how to manually validate our arguments and throw errors, because I'll show you how argparse can do part of what we need, but we're going to need to do a little bit more. We're going to be using a list as a stack, which is a computer science term for a list of values that we want to manipulate. We are going to write a generator function. So we talked in the last chapter about the reversed function is a generator. And so we're going to learn how to write a generator. And then we're going to learn how to write a recursive function, if you've never done that. And we will see why recursive functions can be very, very slow, and how we can use a computer science idea called Memoization to fix that. And that's going to lead us into some esoteric part of Python, which is called function decorators. So let's get started. If you are just coming into this, you will need to go into the top level of the BioFX Python GitHub and source activate the virtual environment. And if you say which Python 3, you should be using the one that is in the virtual environment. I've already done that for these two windows. And with that, I'm going to copy solution 1. I need to go into 04 and then copy solution 1. it doesn't really matter which one I use. I'll use the list function to a program called fib.py, and then I can run PyTest real quick and make sure this function, this test, this program passes all the tests. And let's see how this function works, how this program works. If I run this with -h, it wants 2 arguments for the generations and the litter. I could have called those n and k to follow along with what we saw on the Rosalind site, but I wanted to be more verbose, so it's clear what these numbers mean. So I use generations and litter. You can do what you want. And it's important, these numbers, n and k, generations and litter, need to be less than or equal to 40 and less than or equal to 5. And so how can we write that? Let's just see how this runs. If I try to run this with a value that's not an integer value, you see here that I'm getting this really nice error message, invalid end value, and it tells me exactly which value, foo. And there's something subtle, I've mentioned this before, but that failure there not only printed a really nice error message, but it also indicated to the operating system that the program itself failed. And I can know that by looking at this special bash variable called $? And that is the exit value of the previous process. Now, we've talked a little bit, especially in the context of testing, that an exit value of 0 is actually good. If we think about it, it's like 0 errors, and any non-zero value is an indication that the program failed. So I can see if, for instance, I say echo hello, that it does echo hello, and if I look at that special variable again, I see that the exit value from that process was 0. And that's very important to our testing. We always want to see 0 when the program exits normally, and we want to see a non-zero value when it errors out. It doesn't matter to us what the value is. The fact that this is 2 is not important to us. What's important is that it's not 0. So we have another thing here. If we try to run this, so if I run this with fib 5 and 3, I see it does print 19, which is what we expect for 5 and 3. We expect to see 19 from our program. And if I were to instead pass 3.2, we see here that this is also an invalid integer. 3.2 cannot be parsed as an int. 3 also, even though you could truncate it down to the integer value 3, it still does not follow the pattern of an integer because of that dot. So this is actually, we're getting this from argparse. It's very, very nice. Just a moment here I mentioned this in a previous video, but the 5 here on the command line, to our eye, it looks like the number 5, but it is not. It is, in fact, a string that's being passed. All the values on the command line are strings, and it's up to our program to interpret those strings correctly. And so I'm going to show you how to ask argparse to parse those as integers and create those error messages for us. Some other things about our program. So the way that I've written this is if I run this, like say with a -3 and 2, I'm getting a very nice error message that says that -3 is not good, and additionally I'm saying that this value needs to be between 1 and 40. And if I go look at that value again, I see again it has exited with a non-zero value. And the same with if I were to run this with say 5 and 10, that litter size is too large. It needs to be between 1 and 5. So those are some really good error messages, and I'm going to show you how to implement that right now. So I'm going to start off by doing new. I'm going to get rid of my fib. I'm going to say new py. The purpose of this is Fibonacci. Actually, I never remember how to spell it. I think it's like this, Fibonacci sequence. And I'm going to call it fib.py. And if I look at fib.py, it is the normal structure that I've seen. I want to change this though to generations and litter. And both of those are going to be ints. And I don't need the other values. So that is what I want to generate for my arguments. And to do that, I'm going to use two positional arguments. And I have an example down here of what it looks like to have a named argument that is of the type int. If I get rid of this and I call this generations, because I've gotten rid of the leading dashes, this is now a positional argument. And this will be, what do I have here? Number of generations. Number of generations. I could use a, let's see, do I have a metavar? Yes, metavar here is I'm specifying generations. So this is what we'll print. And the key part here is that I'm saying the type is going to be of integer. Now, if this were an optional argument, I could set a default, but because it is a positional argument, I'm going to make this required, and it does not have a default value. And with that, I can copy and paste that and do the same thing for litter. And this should be, I think I call it like size of litter. Size of litter per generation. That is a really good help message. Proud of myself. And the metavar here is going to be litter, and the type is going to be int. And let's see what we get for that. Generations is going to be equal to args.generations, and then litter is going to be equal to args.litter. And with that, I always just like to generally print args. And let's see what we have so far. So how did this work? If I say fib 5 and 3, I see args generations 5 and 3. Great. If I try to do that 3.2, we get that nice invalid integer value. If I say foo and bar, then it dies on the first one. It says that's an invalid integer value. But if I do the other error messages where I was showing, for instance, where the numbers were outside of the range, let's see. So this n needs to be less than or equal to 40. So if I said 110, those values are going straight through. They're not generating those errors. So I'm getting some of what I need from argparse. How can I get the rest of the checks? Now, let me show you a really, really nice thing that you can do inside of this. This is one of the reasons why I have a getArgs function, is that this is the only place where I want to be using the parser. And so while the parser is in scope, and it's only in scope during the life of this function, while I have access to the parser, I can call something called parser error, and it will generate those nice error messages that we've been seeing from argparse, but I'm doing it in a custom way. So I'm going to copy and paste this line, and then we're going to talk about it for a second. So I have to do this inside getArgs while I have args. And let me indent that. So if it's not true that args gen, interesting. Oh, I see. I called it gen here. I need to fix that. So gen, and that means that it's going to change here. So if it's not true that gen is greater than or equal to 1 and less than or equal to 40, I'm going to call parser error, and I'm going to pass it a custom error message. And I'm going to say generations, and I'm going to show them in quotes what is the value that the user gave me. And I'm going to say this must be between 1 and 40. And if I add that to my code, and then I try to run this, I see I've now created a very nice error message. You see that because I'm calling parser error, it printed a short version of the usage, and then it printed the error that I said here, generations must be between 1 and 40. I iterated back to the user what the offending value was here, And if I look at that echo dollar question, I see that it did exit with a non-zero value. So I got all of that for free, essentially, by calling parser error. Such a nice way of generating error messages, but I have to do it while I have the parser. So I consider all of this one unit of computation here. This is me trying to get and validate the command line arguments. And so at this point in my program here, if I'm able to call get args and I get back the arguments, then I have some assurance that everything has been parsed into the correct types. I have put it into this class of args where I have this type information that I can use programs like TY to check that I'm actually putting in the correct types that I've defined. And so at this point, I feel like I've done a lot of work to ensure that I've got good input that I can use going forward with my program. So the check of the litter size is pretty much identical. I'm going to, before I create that, I'm going to check that the litter size is between 1 and 5. And so let me just comment these out for a second. Let me run pytest-xv. I believe that I have tests for bad generations failing. So let me take that away and verify that I do pass that test. So bad generations, it passes now. Bad litter size, if I have that also passes. So now I'm passing 4 tests that verify that I'm not allowed to use bad input values. So there are tests that check, does your program disallow bad generation and litter size, and does it print a good error message, and does it exit with a non-zero exit value? So with that, there's a lot of explanation here, but with that, I now have something that I can really use to move forward on my program. So if I were to run this with 1 and 2, for instance, I see now fib 1 and 2. I'm showing here, I'm just printing generations 1 and litter size 2. Great. Here I've actually just went to the effort of printing them out on separate lines, which is fine. But the point is, I now have the shell of a program that really does quite a bit of work in validating the input from the user, and I can now go forward with writing a program. So let's start with an imperative approach to writing this, and hopefully it will become apparent as I discuss this what it means to be imperative. And I have a pretty little picture here that gives you an idea of how this growth works with the litter size, and I'm showing here a litter size of 1. Wouldn't spend too much time, it's not a very scientific picture, but maybe a little bit of math here will help. So the Fibonacci sequence, if we consider this f, the f value for any n, any number n, is going to be equal to the addition of the previous value and the one before that. So the last 2 values are what are added together to create the value of the Fibonacci sequence for any value. So a data structure in Python that will allow me to keep a sequence of numbers in order and refer to them by their position is a list. And so I can, I'll go into the REPL here as I am wont to do, and I will define my Fibonacci sequence as always starting with 0 and 1. We saw in the last chapter when I was talking about reversing that I can talk about the value of a list, the last value, by using -1. And I can use also -2. So for the second to last value in the list. So that is a way right away that I can use a list as this data structure that will give me the last 2 values. So F3, the next value in fib, is going to be equal to those 2 added together. Additionally, though, I need to add in the liter size, and most of the time you're going to see Fibonacci written with a liter size of 1, and you don't actually have to take this part into account. But for this problem we do. So given a liter size of 1, the last value, two values ago, times the liter size is going to be equal to 0, because we haven't gotten to an interesting point yet. And but what we want is to do this little bit. We want to append to the Fibonacci sequence the value 2 ago times the liter size plus the value 1 ago. So if I copy that and paste it here, I see that fib is now 0, 1, 1. And if I execute that again, now fib is 0, 1, 1, 2. And as you can tell, I could just keep doing this for the number of times that I need in order to get to the value at a particular generation. So if the generation is 10, then looking at our little bit here, f at 10 is going to be equal to f at 9 times the liter size plus f at 8. And so we would just keep doing this until we got to 10 generations and then stop, and that will be the answer to our program. And if you want to go off at this point, you now have enough information to write a program that passes the test suite, and you can move on if you want. But stick with me to talk about a lot of very interesting ideas from computer science that we can apply to writing this program. So I'm going to start off with, I'm going to rewrite this here. I'm going to redefine fib is equal to this. I've already done liter is equal to 1. And I'm going to show you how to write a little loop to generate the Fibonacci sequence for the number of generations that we want. So if we define a liter size of 1 and the generations is 5, then I can use a for loop to go over I need to go to generations minus 1 because we are in a 0 offset based language, so we don't actually want to, we would go 1 too many, and there are there's so many jokes about basically off by 1 errors in programming, but this could be 1, and so I'm going to go for it doesn't matter what this value is, so I'm using this is a legal variable name of the underscore, but it also is an indication to tools like linters that I don't actually care about this value. I'm only calling this for the side effect of doing this a particular number of times. So I'm using the range operator. So if I say range of 10, it actually returns just a range. This is a generator. It's another lazy function. So if I say list of that, range 10 gives me the numbers from 0 to 9. So that is a list of 10 numbers, but it does not include 10. So what I'm using here is I'm saying for, it doesn't matter what I call this, in the range of generations minus 1, then it's going to do this 5 times. I want to call that bit of code where I append to the Fibonacci sequence 2 positions ago times the liter size plus the position 1 ago. And if I look at that, what is fib? It has now been expanded to the list. So I was doing that manually before, but now I've written a for loop to do that for me. And the answer to this is 5. It's simply the last number in the sequence. And that is enough right there to create a working solution. So I recommend that you stop the video here, write your working solution, run make sure it passes all the tests, and then go read the tests and try to understand what's going on, and then come back here and we'll talk about some more interesting things. So with that, let's go over some of the solutions. We've already seen that I can take this code and pop it in to my program. So I've called mine fib, and I've already done all the get arg stuff. And so I'm going to paste this in, get the indentation correct. And this is exactly what I had in the REPL, starting off with 0 and 1, going through the generations and appending to this the next values. And so if I run fib with 5 and 3, I should get 19. And that's not a bad solution. I want to point out, it does keep up with the entire Fibonacci sequence up to that point. So it creates, if we were to go up to the maximum value of 40, we see that it's going to create 40 values. We have arbitrarily put 40 as the max. I could do 4,000, right? It doesn't, if we go just for a minute here, let's take away this, this check, and that will allow us to create, for instance, 4,000. Then you see it's printing a list of 4,000 values. And that is not always, it's often a bad idea. If the only value that we care about is the last one, or in the generation, we really need like the last two and then the current one. So we really only need 2 values. There's no point in tracking the memory for 4,000 values or 10,000 or 1,000,000. So you can see, you could foresee that this could create problems if we were dealing with very, very large values. Now, to be fair, I write a lot of high performance programs in bioinformatics, and I would not reach for Python if I was really worried about performance and memory usage. I would probably write it in Rust, and I will have a series of videos coming about that to show you how to use Rust. So, take this with a grain of salt. Python is not necessarily a high-performing programming language, and if you really care about memory usage, you probably want to use a different language entirely. But it still gets at the idea, even if you're new to these ideas, that keeping up with all of the values in the Fibonacci series is not necessary for a program to work, and it could in fact lead to some serious performance issues. But that said, premature optimization is the root of all evil. So if this works, and this does certainly work for our problem, and you understand this solution, then that's fantastic. And if you get to the point where you actually encounter performance problems with your programs, that is when you should worry about optimization, or, for instance, perhaps just rewriting them in a language that's more suited for the task. So don't worry about it until you actually need it. And a lot of times you won't need it. So the important parts of this loop here that you need to understand, this is a variable name that I'm indicating that it's basically a throwaway value. And I want to show you what, if I were to say for x, doesn't matter what I'm calling it here. If I were to run this, if I were to see ty check on my fib program, it says, yeah, there's no problem. But if I call pylent on fib, then you'll see it says there's an unused x value. Actually it tells me here there's an unused text IO. I don't need text IO. So great job. Thank you, pylent. I will remove that. And if I run this again, it still says there's an unused variable. And that is not a bug. It's just telling me that it's basically a smell check, right? Like you've created a variable and you're not using it. Is that a mistake? If I change that to underscore, then that goes away. I'm now at a 10 of 10. And so this is a way to indicate to the reader and also to linters that you don't intend to use this value. So a good thing to know about. I'm using the range operator here, which we've not used before, to create an iterable that will go the number of times I need it to be, which is generations -1. And then I'm using this, and I talked about this before, I'm using this method of instantiating a list of some sort of a value that's, a variable that's going to hold the values I care about. And then I'm using a for loop to mutate that value. And I don't love this approach. It's a very imperative approach, but it does work, and I'm very careful here, and there's only a few lines of code, so I can be pretty reasonable that I'm not doing anything stupid here. So the reason why it's called, I keep using the word imperative, is because I'm really indicating every single step of this line, every single step of the algorithm, and there are more declarative ways that I could write this, where I let the programming implementation kind of take care of some details for me, but it has some unintended consequences that I'll have to deal with. So here's a slight variation on this code that I have here. I can actually create a function inside a function in Python. And it's kind of a weird thing to do, but I want you to be aware of it because you may encounter this in other people's code, or you may actually have a reason to want to write this. And this is creating something called a closure. So I'm going to create inside of here I'm going to create a fib function, and it's going to take as its value, as its argument in, going back to the number n, meaning generations that we saw in the description on the Rosalind page. And this is going to return an integer. And all of this code here that was just living inside of main has now been indented so it only belongs to the def fib function. Now, perhaps you see right away there's going to be a problem here. I'm defining a fib function, and before I have this fib list, and so I can't do this. I need to first off, it's just confusing for me as the reader. So I need to change one of these. So I'm going to call this one nums. And so I can actually say I'm going to substitute every fib here for nums. And so I'm calling it nums is equal to 0 and 1, and now nums is going to append the previous one times the liter size, and then the one just before it. And then what this is going to return, I have to return from my function. If I don't have a return, it's going to by default return none. So I'm going to return the last value from nums. And instead of printing this, I'm going to say print fib args.generations. Now, what's important here is that the reason why I'm writing it this way is because it's closing around the value for args.liter. So the only argument to my fib function is the number of generations in, and that's the point of this. I'm not passing this as a parameter to the function because it's creating a closure around liter. If you don't get that, why that's important or interesting, then don't worry about it. I'm going to show you a way to write it in a different way. But why would I want to do that? Well, one of the things that's interesting is that this fib function is only available inside the main function. And sometimes you want that. Sometimes you want to create a function that can't be called by any other part of your code. Or maybe you just want a function that creates a closure. And I'm closing around one value, but maybe you want to close around several. And it makes the signature of your function much simpler. Instead of taking 2 parameters, it's only taking 1. So does this work? That's the most important thing. Does my code work? Let's run pytest-xv and just determine. It does. So this works, but also the previous version where we just had it like this, that also works. That's the point of having our tests, is that we can keep playing around with our program and refactoring it and to try to determine what is the solution that we like the best. So another way to write this would be to, if I go back to the way I had that, whoops, well, I'll just copy and paste this. Let's just take this, and I can paste it in as a function. Now I have to fix the formatting. But I could, for instance, if I don't want to create a closure, and I'm a little bit picky about my code formatting. So with this version, I want to have I've moved all of that code into a function. And what's nice about this is now I can write a unit test for this, right? And we saw that in the very first chapter. I moved that count bit into a function called count, and then I wrote a test for count, and I used that over and over again. And that was clearly overkill for that program. The function count basically was the entire program. And as is the case here, this is just generating a Fibonacci sequence, and now I've written a main function that calls a getArgs function that now calls a fib function. So this is clearly kind of a ridiculous way of going about this. But as your programs get larger and larger, you're going to have very complicated functions that do perhaps too many things. A lot of times you really want your functions to just take one or two parameters so that you can test them independently and then make sure that they work correctly and then compose them together into larger programs. So why would I want to go about creating a fib function here? Well, it is really straightforward here. I'm not creating a closure now. And so it's very clear that I'm taking in and the liter size, and I could write a function for that. And so this is a way of writing the same idea but without a closure and putting it into its own function that's now not hidden inside of main so that it can have a unit test. If I had this written as a closure, this version of fib, I could not write a unit test for it because it would not be visible to the rest of the program. So some interesting things to note about how to write programs. And so moving to our next solution is that we're going to write a generator function. So we haven't seen this before, and it's a pretty cool idea. The idea of a function, why do you want to write a generator function? It's because we're creating a list that is infinite. And so it's not possible for us to write a straight up function that produces an infinite list because it would never finish producing that infinite list. We can, however, write a function that uses a specific, very specific term to Python called yield, and it will essentially stop when you call the function, when it hits a yield, it will return that value. So we saw before that from our function we need to return a value, and that exits the function right there. And the next time we call the function, it starts with a new state. It will start with nums here being reinitialized to 0 and 1. But yield is a particular way of executing the function. Here, the first time this is called, we're setting x and y equal to 0 and 1, and then we're yielding x. And then the function leaves and returns this value. The next time fib is called, it picks up from where it yielded and then goes into this while loop and will yield y. And then the next time this is called, it will pick up from here. It will set x and y equal to y times k, and then x plus y, and then go through the loop, yield y, and then the next time that's called, it will continue to do this loop. So this is a way of writing a generator, and this yield essentially freezes the state of the function and then resumes the function at that point. It's kind of amazing. This works really quite well. And so the signature for this function is that it is a generator. So to use this, I'm gonna jump up to my typing module, and I'm going to import generator. And I'm going to go down here, and I'm just going to copy and paste this. Actually, it'd be easier if I get it from the generator. Let me just open up my solution generator and grab this version of my function. And now I definitely do want this to be its own separate function because I'm using this yield syntax. And so with this, I've now imported this generator, and the generator has a type signature where I want to indicate that it yields an integer value. So that's what this int is. That's what it yields. And the send and return types are none and none. We don't need to worry about that right now. If you really want to get into what it means to create generators, you can learn more about those. And, you know, honestly, if you don't like the type signature, you don't have to indicate any of that. You could also just write it like this. And if you mix type signatures, type hints in the signatures with ones that don't have it, that's completely fine. It doesn't matter. We're just trying to learn some computer science and some bioinformatics here. So, you know, if that part is confusing to you, just skip it. It doesn't really matter. But this is technically a generator, and the yield is what makes it work that way. So what's extremely cool about this solution is that we are no longer keeping up with the entire list of the Fibonacci sequence. We're only saving the last two values that we need. And the first number is 0. And so that's where we set x and y equal to 0 and 1. We return 0. The next time we return y, the second value in this list. And then we change the x and y. We overwrite them with y times the size of the k that we've passed here. And notice that we're not passing in now. We're going to call this as many times as we want. And it's going to use the k that it was initialized with. And that y is going to be equal to y times k, and x is now going to be equal to x times y, and y will have already been multiplied by the liter size. So that is what is going on here. This creates an infinite loop, and it will only yield one value at a time. So this acts like an iterator because it's producing the values only as they're requested. So we could call this 40,000 times, we could call it 1,000,000 times, and it will never use more memory than it needs to store just the last two values. And what's going on here, it shows you as you initialize this with different k sizes, it's going to start off the same, 0, 1, 1, but then this 2, in this generation, this is going to be 4. Here it's 3, but in this generation, it's going to be 7. And so this is, we get to 19, which is our expected value for a k of 3 for generation 5. So we see how the numbers work and why this how the generator's state changes over time. Sometimes it can be really useful to write this out for yourself to kind of prove that you understand how it's working. So we have our fib. The way that we use this now is to create this generator object. So it changes the syntax here that the generator is going to be equal to creating the Fibonacci generator using the liter size that we want. Now we need to call that generator as many times as necessary to produce the next value. To show you how this works, I'm going to do something real quick. I'm going to go into the REPL, and I needed to get rid of those new lines so that I could, and actually let me get rid of some of these type hints too for a second. Let me grab this, and I'm going to define a Fibonacci generator. And I'm going to go back and put in my code the way it was, and I want to show you, I'm going to call gen is equal to fib with a liter size of 3. And if I call, what I'm showing here is I'm calling next on gen, which is a function that's built in. If I say help on next in Python, it says return the next item from an iterator. So this works on any iterator. For instance, an iterator over the lines in a file. It'll work. We have just now generated, we created a generator, which is an iterator. And so if I say next of gen, it gives me 0. And if I call that, it gives me 1. Now it gives me 1. Now it gives me 4. Now it gives me 7. Now it gives me 19. And that is the progression that we saw here. 1, 1, 1, 4, 7, 19. So that is what is going on here. I'm saying give me the sequence. The sequence is going to be set to calling this, and I'm using I'm calling this for the correct number of generations. So I'm using a list comprehension again, where I'm sticking my for loop in here at the end of it it doesn't matter what I'm calling this, in the range of the generations that I want, call the next from the generator, and then simply print the sequence there. So this is actually building up the sequence, and so this will now go back the other way and store the whole sequence in memory, and I'm going to show you how to get around that. So using that, using this generator, I can build up the entire Fibonacci sequence, and then I can print the last sequence. And I will prove to you that we have the whole sequence in there. So let me go back to running fib 5 and 3. I have the whole list there. So if I go back to doing 40, then you see I have 40 numbers. And again, the whole point of writing this generator was so that I don't have that. So let me show you a way of getting around that. What I can do is I can go back to my for loop, and I can initialize an answer, the final answer that I care about. The answer is going to be equal to 0. And then I can say for range in the generations that I want, set the answer is equal to the next value from the generator. And then I just print the answer. And that prints that. Let's go back to 5 and 3, which I know about. Let's do a little PyTest on this. And I pass all the tests. So now I'm only keeping up with the last answer, and this generator is only keeping up with the last two values. So if I were to use some tools for profiling memory, I would be able to see that I'm using really not very much memory to generate this answer. So that is another way of writing this, but I brought this up in order to bring up this function called itertools islice. And if we were to Google for Python itertools, probably yes, we will find here that this has a bunch of functions creating iterators for efficient looping, and we're specifically looking for one called islice. So if I look for this islice, it gives me some ideas here about how to use it. It will slice out the elements from a sequence going from start to stop. It looks a lot like a list manipulation. And so what we have here is another way that I could write this. And now this is getting kind of esoteric, but I need to import this function. So let me go up here and say from itertools import islice, and I may or may not have to install that. I think it's not a standard function, but I can create my sequence by calling it like this, and then I'm back to getting the entire list here. And the first argument to islice is the function that is going to be called, and the second argument is the number of times to call it. And so this is going to be lazy, and so let's just see what we get here for, if we print seek, what do we see from here? Let's go back to 5 and 3, and we see that we are storing the entire array in memory again, but this is essentially another way of writing the list comprehension, is this using this islice. So you may or may not find that useful. I think that maybe I was just looking for every possible way to show you that you might find interesting. So this you could actually get this down, golfing down to one line of code by calling this function. And just having it one line of code, but I gotta say, I don't find that very readable at all. And if I run my PyTest, then I do see it passes, but this is getting to be pretty esoteric. But it's interesting. I love this quote from Spinal Tap. It's such a fine line between stupid and clever. So this is another way of writing this, but I don't find it very readable. So I would probably stay away from this. What is interesting, though, is to write this in a completely different manner. I'm going to show you using recursion. So I'm back to writing a closure inside of my function here, and so we're not going to be using this, and I no longer need the iter tools, and I don't need the generator anymore. So what I've got here, and I'm going to get this from, let's see, it is my selection 3 recursion. If we look at this version, I'm going to copy this, paste it right here. I have written a fib function that takes as the size, the liter size, the n, and I've written it in such a way that it's going to return 1, the value 1, if, now we're back to using an if expression, you see here. Return 1, this is what to do if this is true. So if n that I've been given, n here is the generation, not the liter size. We're going to return 1 if n is either 1 or 2. Else we're going to return calling fib for n minus 2 times the size of the liter, and then adding to that fib for the previous one. And so this is essentially exactly what we saw when we wrote out f3 is equal to, f2 plus, or f at n is equal to f at n minus 2 and plus f at n minus 1. So we've essentially been able to write out that exactly, almost mathematical notation, which is really, really cool. And so we can call this for the number of generations that we want, and we should get the answer. And does this work? Let's find out. Fib 5 and 3. It is slow. Let's see. I did not print it. Let's try that again. It does print 5 and 3. Again, we run PyTest. PyTest. And this version does work. It is a classic recursive function and a classic way of writing this, and that you will encounter in so many introductory computer science classes. But it is not necessarily easy to understand, especially if you've never seen recursion before. But you may come across something like this, and if you do, I want you to understand why this could be very difficult to work with. And again, we see that the reason why I have written this as a closure is so that I don't have to pass args.liter. You see here I'm passing args fib.generation without passing. If args.liter wasn't a bound here, I would have to pass args.liter to every other call of fib, and I was just trying to make a function signature that only took the generation that I cared about, the n for the number of generations. And so that was why I wrote this as a closure. But again, the problem with writing it as a closure here is that now it's impossible for me to write a unit test. So you have to take that with a grain of salt. When you write your programs, you have to take these matters into consideration. Let's talk for a moment about why this is actually a pretty terrible way of writing this from a performance standpoint. And again, premature optimization is the root of all evil. If for the purposes of the programs that you write in your lab for your work, for your research, if they work well enough, then that's fine. A lot of times in bioinformatics, we simply throw more hardware at a problem instead of trying to make the programs run faster. So if it doesn't use memory very well, just maybe run it on a machine that has a lot of memory. And if you're just trying to get an answer and move on. If you're actually trying to produce software to release to the world that needs to be efficient, then you need to worry about problems like this. And so the problem here is that on the way of calculating fib of 5, we actually end up calculating fib of 2 3 times. We see it here, we see it here, and we see it here. So we're doing that work 3 times, and it gets much, much worse. The higher fib becomes, the higher this value, the more times we call these other values over and over again. And so it really, really increases the performance of our program. It increases the time for our program to run. And so here I have from Bash, what I show is I'm for values of 10, 20, 30, and 40, I'm running the recursive version with that value and a liter size of 1. And what we see is the answers. It's printing the answers, which is cool. But because I'm calling time in front of it, it's showing me how much time is being spent here. And the big thing here is that there's a huge jump between this value for 30 and this value. Like, it was really very negligible up until 40. And then we see this huge leap. And we're talking, 31 milliseconds. So it's not a lot to, or 31 seconds, right? It's not a lot to worry about. And let's just see what that looks like. So if I run this fib on 5 and 3, it takes 19. So let's do 10, and let's do 20, and let's do 30, and then let's do 40. And we see there is a significant change. Like, everything was fine. I would be fine running a program with those, but now all of a sudden I'm waiting quite a bit of time to finish that. And if I time this on my computer, I'll let that run for a second, and we'll watch to see how long it actually takes on this little bit newer computer. So how can I get around this? Okay, so there we see it took me 10 seconds to run that on my computer. So and even for just a one-off program, that might be fine. But if you're going to run this on a huge input data set, and something like this has to run for days or weeks at a time on an HPC, you're just wasting time because you've written an inefficient algorithm. So let's talk about how you can make it run faster. There's something called memoization, where we essentially we create a cache, which here I'm going to use a dictionary, and I can look up in the cache for the value that I'm calling this with. So for instance, the value is going to be this 5, and I can say, have I ever calculated the value for 5? Does cache is 5 in the cache? And if it's true that 5 is not in the cache, then it's going to say, okay, the cache for 5 is going to be equal to calling that function, which we're just calling f. F is being the callable thing that I passed in here. Call that function f with the value of 5, whatever I'm calling, and set the cache if for that value to be the answer, and then return that value. And then when I come back through and I call that for f of 4, it will say, hey, I've never seen f of 4, so call this for f of 4 and cache that value, and on down the call stack. And so 4 will go to 3, and then as we get here, eventually we're going to calculate 2. 2 is going to store this value, and the next time 2 is called, like maybe over here, it'll say, oh, I don't need to actually recall this function again. I have a cached value for 2, and so I will use that. And so for this call and this call, we actually use the cached value. And that works really well. So that version is called Memoize this. And so if we go to our memoized version and we take this version, we copy our memoize into here. Now it's going to change the way that we call our function. So we're still creating our recursive version right here, but then we immediately memoize it. So we overwrite fib with a memoized version of fib, and then we call this. So first off, does this work? It doesn't matter how well it performs if it gives us the wrong answer. Let's see. I have something wrong here. Let's just see. Okay. What have I messed up? Well, I tell you what, I'm just going to copy copy my memoized. I must have done something wrong there to py. Sorry. Copy. And then if I run it with 5 and 3, do I get 19? So I did some sort of copy paste wrong. So sorry about that. So I have still defined my recursive function, but then I immediately memoize it. And now when I run this, I still get the right answer, but if I go back to my time and I run that, now I'm not taking 10 seconds. I'm taking 0.04 seconds. So much faster, dramatic change in the performance, and it's all because I'm just using a little lookup. And we've talked about in the last chapter, we talked about replacing a decision tree with a lookup table from a dictionary. And it's exactly what I'm doing here. I'm creating a cache table. Basically we're creating a closure again. So Memoize is closing around cache, and Memoize is returning a new version of this function where instead of calling the function directly, it's actually calling this closure here, where closure is closing around cache, and it's returning the cached value and caching it along the way if it needs. And that's why this works, and that's why I've gone to the trouble of explaining what closures are to you, because that's what Memoize is doing. It's making a closure around this cache value. So that is why our program now performs pretty darn well. So with that, there is another way of writing this idea, and that is we have our we can override it, but we can also use this thing called a function decorator, which I'll be honest, I don't like. So I'm going to go in here and I'm going to add this Memoize. And what's interesting is I no longer have to write it with overriding it like that. Now this Memoize is being applied to this function. It's going to be a memoized function. Let me make sure I save that. And let me run my test. Does it still work? Yes. And it still works very well. So it still passes all my tests and it still performs at the same level. But now instead of overriding the function with a memoized version, I'm now using this thing called a function decorator. And I never use these really in my day-to-day work, but you will very likely encounter function decorators as you're reading more advanced Python code. And so when you see this @ sign in front of a function definition, that is a function decorator. And you can now have the terminology to go look up what is going on there. We went to the trouble of writing this Memoize function, but it turns out we didn't even need to do that, because in this function, module called functools, there is a function called LRU cache, for least recently used cache. It's a nice fancy computer science term. You don't really need to understand what it's talking about, but essentially I don't need to even write my Memoize function. This is such a common idea from computer science that it has already been implemented many times. So to use this, I decorate my function with LRU cache, which is a function that I've just imported. And now I'll go back, I test. Yes, everything is fine. I time my program. Yes, it still works. Actually, even better. We were saying 0.04 seconds, now we're saying 0.01. So very much a win. We wrote something that is fairly readable if you are familiar with recursive function definitions, and actually reads a lot like math here. And we were able to fix the performance problems by simply importing a function from a module that was already written for us, and we were able to just decorate our function with that, and we got a great solution. I'd like to talk for a little bit about the testing. I think there's a lot that you can learn from the tests that I've written, and one of the first things that I'd like to look at is how I go about testing the bad values for generation and litter size. And inside of my test program is a function called test bad in to ensure that our program dies when the number of generations is bad. Maybe I should have called this bad generations. And for that, I'm bringing in the random module, which I'm going to talk about here in just a second. But real quick, for value of n, I want a random choice that is coming from a list of negative numbers, from -10 to 0, and then a list of numbers outside of the range. So remembering that we want a number generations should be between 1 and 40. So negative values, 0, 41, and anything greater, those are all bad values. So I'm making a choice of n, the number of generations, to be from something that's definitely outside of that range. And what's interesting here is if we go into the Python REPL and we look at what is, we've already looked at range. So let's look at range of -10 to 0. That's just going to give us a range generator. So I can force that into a list, and you see here I've gotten now a list of numbers, negative numbers. And the other list is a list from 41 to 50. And so those are all bad values. And what's interesting is that I can add those together and create one list of all these bad values. And then I can import the random module, and I can say make a random, so let's put that into a bad in. And if I say random choice from bad in, I will get a different random choice every time. And all of these would be suitable for feeding to my program to ensure that it dies with a bad value. So for k, I want something that's valid. So that is for the numbers between 1 and 5. Those will be fine. And so I run the program with these values of n and k. And what I want to ensure is that my return value is not 0. And then I'm asserting that the output begins with usage. And then I'm bringing in the RE module, regular expression, which we've talked about a bit before. And I'm searching anywhere in the output for the string n must be between 1 and 40. And so that is how my program is working to look for, to ensure that my program dies with a bad value for the number of generations. And I essentially do the same thing for the bad k value as well. So I do want to ensure that my function runs on good input. So I have an instance here where I'm running it with values of 30 and 4, and I know, for instance, that is this is the answer I should get. And so obviously I don't necessarily want to have every single possible value between all the combinations between 1 and 40 and 1 and 5 for n and k, and I could do that exhaustively, but that's a bit much. I'm just spot checking here with a few that I know are correct, and I started with that first value of 5 and 3. I know that should give me 19. So that is often how I'll write tests, just kind of spot checking to make sure that I've covered enough bases. Often I will at least ensure that the absolute values of the ranges, so if it's from 1 to 40, I will definitely test with both 1 and 40 and maybe a couple of other random values in between. And it's important to me to use random values. I point out here, part of this comes from writing for students so that they don't just end up writing programs that only look for a specific value that was in the test. I make sure that it's giving some random values so that they actually have to write tests, programs that respond to a broader range of input. But it also helps me not to accidentally code for some specific value. So random is a module for doing that. We also see here I could use a function called random int that just gives me a random integer in that range. Another very useful one to use. In this case, it's completely fine for the k value because it's a contiguous sequence, whereas for this I was trying to create a non-contiguous sequence of numbers that included numbers outside of 1 to 40. So that is a little bit about randomness. I think it's great to include randomness in your testing if you can. A note here about running the test suite on all of the solutions I wrote. Here is the make file that I have in here. Actually, it looks a little different. I've decided to get rid of the pylint and MyPy tests because they simply don't seem to work very well anymore. So I'm using this simpler version that only is using Flake 8 additionally to check. And what's going on here is that when I type make test, it's going to run specifically the test suite on whatever is the current fib.py. And that's useful. It helps me to test as I'm going along. So I could type make test, and it runs, that entire test suite. And this was more important when I had all this extra stuff with pylint, but it's less important now. You really can get what you need by just running pytest.xv. It's just fine. So, but while I was writing this book, I wanted to ensure that every test that I had, every solution that I had passed all the tests, and I don't want to sit here and copy each solution to fib.py and run make tests. So I wrote a program, as you can imagine, it's in the bin directory and it's called all test, and this looks very similar to what you've already seen, and it takes the program that I want to test and it looks for all of the things that look like solution.py to run. And so let's take a look at how this program works. There's some juicy bits in here that you can definitely use to run, to include in your own programs. One of the first things to note here is that I can get the current working directory from this OS get cwd, current working directory. And I use that because I run this, if we look at my make test, my make file, if I run the all program, it assumes that I'm in this current directory, so that the path to all test is going up two directories, one to the parent and then into the bin directory, and then inside the bin there's an all test. So when I execute this, my current working directory is this directory right here, the 04 fib directory. And so when I say get current working directory in this program, it's going to be the directory here, the 04 directory, this one. And that's important because I need to look in this directory for things that look like solution.py. So it would look like solution_.py. On the command line, this is called a glob, a file glob. And so bash, or in my case, ZSH, is turning the star into any substring. So solution, and it doesn't matter what occurs between that and the star and the .py. Star is 0 or more of anything at all. And so that's useful. I want that same kind of action going on. I want to find all the solution.py's in my current directory. And of course, there are some other files in here that I want to skip over. And so this complicated little bit here, it reads pretty well, but there's a bit here to unpack, and I want to spend a little bit of time doing that. We see here that I'm using a filter operation. So this is one of these higher order functions that I haven't really talked about higher order functions much, but it's a function that takes as an argument other functions. Very, very useful. And so what I'm doing is I'm filtering the OS lister for anything that looks like is a match to this regular expression, something that starts with solution, and then this regular expression is a little more complicated than the file glob, but I'll explain it in just a second. So the solutions that I want to test are filtering for things that look like this, the contents of this directory. So let's take this one step at a time. Let's import OS, and let's say OS dot, let's first get current working directory is equal to OS get cwd. Current working directory on my computer is this path. And so if I say OS lister on the current working directory, these are the files in here. Now I only want the files that start that look like solution.py. One of the ways I could do that, I could use a list expression. I want file for file in. So if I just do this, it shows me all the files. I could say if file starts with solution. And you see here, it actually only finds the ones that are solution. And I could additionally say and file dot ends. Let's make this window a little bigger. Ends, oh boy. Let's see. And file dot ends with, oh boy, that's really not gonna be okay. Let me start again. Import OS, get the current working directory, and let's see, and file dot ends with .py. That is one way of writing this, but I can instead bring in the RE module to create a regular expression to find those things. So this is a pattern that we haven't seen yet. It is a list comprehension, but it is adding at the end this if statement. So it's a way of filtering for the contents of OS Lister for only the files that start with solution and end with .py. So file for file in this if the file meets these conditions. That's pretty cool. Let's talk about some of the other ways that I wrote this. So moving ahead, so these are, if I just say files is equal to OS Lister, I can actually bring in pprint. And I tried to bring this in before. So let's go here and follow along with what I've got. My goodness, I'm having a hard time copying. Okay, so if I say pprint files, those are all of the files. I don't want all of the files. I could do files is equal to that, and then if I pprint, that is looking better. Let's talk about another way that I could write this. One that uses, we saw here solution start.py is a file glob. Let's try to get that working in our program. And to do that, I'm going to use a regular expression. And I need to explain, we looked a little bit already that in the regular expression language, certain characters are meta characters. So they don't mean what they literally mean. So a dot in a regular expression means zero, it means any character at all. And putting a star after it means zero or more of any particular character. Whereas if I want a literal dot, I need to put a backslash in front of it. So my regular expression for to match the file glob operation is solution dot star backslash dot py, because the dot star means zero more of anything, and then literally a dot py. And the other bits here are literal strings, so they don't have any special meaning in regular expression grammar. These have special meaning though, and so in order to use the dot for a particular reason, I have to understand what it means in the context. So let me import RE for the regular expression module, and then this is a little complicated. I'm going to use this match. So match starts at the beginning of a string, and I'm going to say, is it true that the string solution1.py matches this regular expression? And it is true because it returns a match operator. If I were to put an X here at the end, whoops, let's call it PX, then we see that the solution fails. The reason why this one passed was because it was able to match up to the PY, and it just didn't. You see here, it left off the X. So it is true that this string matches, this string does not match that. It is not true. It is true for the others. So how can I use this? So I can actually filter a list. A filter is a function that we haven't seen before. It's a higher order function, and it takes as its first argument a function. And we can use this special keyword in Python called lambda to create an anonymous function right here. So I can do something that's not technically allowed. This is bad style, but I can actually assign the lambda to a variable. And if I look at that, I can see that this f is this function, and it's actually a lambda. I can say, what is the type of f? And it's a function. This is a function. So what happens is I can call f of solution1.py, and it returns a match object. And if I say px, then it returns nothing. And what is the type of what it's returning? It's returning none. So when the solution fails, it just returns nothing. And if you remember that if I coerce that to a Boolean function, that returns false. Whereas if I do a Boolean of py, then that's true. It's true that it finds something. So filter wants some function that can be evaluated, the return value of which can be evaluated in a Boolean context to determine whether or not to take an element from a list of objects that it's given. So let's just look at this. Let's say, what is files? Let's say files is going to be equal to os.lister, so that we have all the files. And let's pprint all the files real quick. And so we see here, this is a list of everything that's in the directory. What I want is to filter, using f, my files. And it gives me this filter object, which, if you recall, I can coerce to a list by doing this list. And if I pprint that, you see it does only return the solution something.py. And so here I've written with filter with f, and if you remember, f was assigned to that lambda. So the way that I'm showing it written here is I'm putting all of that into just one line. Filter on this lambda, where it's matching solution, given a particular name. So each file goes into name, and the name is applied into this, this operation. So if we look at what that looks like, that is a way of filtering all the files for things that look like solution.py. And I showed you the arguably simpler solution using a list comprehension with an if statement at the end. I can go a little farther than this, and maybe you don't really care about this, but I find this interesting. There's something called partial function application. And to demonstrate this, I'm going to import the operator. So this is a standard module that you can bring in, and there is inside the operator, if we say help operator, we see here that there are a lot of functions that we can call. Add, concat, basically any symbol like 4 plus 3, that symbol is an operator. And it is the same thing as calling operator add 4 and 3. So that's what's going on underneath. This is just called syntactic sugar for something that's actually going on like this. So it's underneath. It's calling this function called operator add. So why is that useful? Well, from the functools module that I've talked a little bit about, I can import a function called partial. And I could create, for instance, a successor function where I am, let's see, operator. I've created a function, and if I say, what is the type of successor? It is a partial function, and so if I call the successor to 1, it's going to return 2. And if I call the successor of the successor of that, it's going to return 3, and so forth. So I have created a function that applies operator add, and it's partially bound with the value 1. So it's giving me the successor, the number after that. I could create one called predecessor, where I'm doing a partial application of operator.sub and 1. And if I say, what is the predecessor of 10? That's 9. Oh, negative 9. Interesting. So because it's doing 1 minus 9. So actually what I would want to do then, I didn't try this before, let's add -1 is what we want to do. So the predecessor of 10 is 9, and the predecessor of that is 8. So that's what partial function application is. Why is that important? Well, I could partially apply my match operator where I'm applying the first argument to match, and if you looked at this match, it wants first the regular expression, and then as its second argument, it's going to take some value to apply to that. So I'm saying, well, let me create a function f that is a partial application of the match operator with this solution, .py, that I'm looking for. And what is the type of f? It is a partial function. Very, very cool. So if I try to call f with no arguments, it actually blows up. So if I say foo, this is something that doesn't match, but solution1.foo.py, that does match. So why is that cool? Because now I can write my filter like this. And so once you understand all these little parts that are going on, you end up being able to write small little pipelines of functions that each individually do some very specific bit and do it well, and then you put them all together, and this actually reads pretty well. I want a list where I filter using this function all these files, and I get back if I understand that the function, that filtering here, what it's looking for, then I'm getting back exactly what I expected. So all of that was really a long extra little tangent to introduce a lot of ideas that I tend to prefer from functional programming. And that's an extremely different way of going about looking at trying to write these kinds of things from the standpoint of optional object-oriented programming. And I think, there was something actually I skipped over here when I started this section of the video. I actually skipped over benchmarking. So let me go back to benchmarking real quick. I have a way here of just on the command line with bash running through each one of these few programs and echoing the program and then timing how long it takes to run with the maximum values of 40 and 5. And we see here, it gives me a general idea of running one time, how long it takes to run those, but that's not very useful. It's not a very effective way of benchmarking the tools. So instead, there's a tool called Hyperfine. It's actually written in Rust, and for this, I installed it on my computer. If you're interested in using Hyperfine, then I would encourage you to go read the documentation on how to install it. But this is an actual benchmarking program, and if you want to get into figuring out which one is the best program, then you would run Hyperfine, and you say for each program in this list, and there's a problem here. There's actually an error. This should be solution one list, either closure or function. That function name is wrong. But if you fix that, then this will run and will give you some output that looks like this. And so it is possible for me to look at this output, and it says here that this solution ran faster a little bit than these other two solutions. And what I can see is that it looks like it did 23 runs of one program, 24 of another, 23 here. Gives me a lot of statistics on how long it took to run each one, but this is much, much better for benchmarking if you really want to get into that. I also mentioned another tool called Bench that you might want to look at. When I wrote the book, this ran it 60 times. When I just ran it here, this time it ran it like 23 times. So it uses a bit of randomness and to try to really determine what's going on. There is also another little bit here that I'm telling it to remove the PyCache directory when it runs this, so that it's not because PyCache is a way of caching the bytecode version of the program, and I don't want that to be a part of I don't want to include that in my benchmarking. So sorry about skipping that. All right, so looking at the end of this, I've talked a lot about styles of programming. And so the first approach that I showed was a dynamic programming approach, where we solve the larger problem by solving smaller problems. And then we also looked at a recursive way, some other ways using recursion and something called higher order functions to pass functions to other functions, which is kind of cool. I point out here that both spoken and programming languages really shape the way we think. So if you only know how to program with one style, like object-oriented, and you're not familiar with functional programming, then it's really going to color the way you see everything as needing objects to represent them. When I would really argue that the world, that programming is a much simpler enterprise when we just focus on functions and writing good tests for the functions. So as a review, in the Git args, one of the things that we did was we performed some manual validation, and we used parser error. That's a great way to create really good error messages for your user and to exit the program with a non-zero value. We talked about how we can use a list as a stack, and we talked about pushing and popping elements off. We didn't really pop. We were just getting the last value by using negative indexing. We talked about the yield in a function. It turns it into a generator. And then we even saw how to write a type signature for a generator. And in that version of the Fibonacci program, we only were tracking the last two values of the Fibonacci sequence. So even if we had to go up into 1,000,000 iterations, we wouldn't be storing 1,000,000 numbers. We would only ever be storing 2. And so generators are useful for creating potentially infinite lists of values. We saw how a recursive function calls itself. That's what makes it recursive. But the problem we also saw is that in doing something like Fibonacci, it might end up calling the same function many times. And so one solution was to use a memoization. We wrote our own memoizer to cache the values, and then we learned about the LRU cache. And in order to use that, we had to delve into function decorators with the @ sign. So now you know about those. We talked a bit about higher order functions. They're functions that take other functions. And we talked about, the function decorators. We talked about benchmarking, and I introduced the tool Hyperfine. And I also introduced the random module in the testing in order to get pseudo-random selection of values that will make our testing more effective because our tests now cover a broader range of values. So that's it for this chapter.